Well, good afternoon, AP Calculus BC. Welcome. It's time for our lesson, but first of all, Edward, happy Chinese New Year. We're all going to wish you what we are. This is our gift. This is our gift to you inside the Great Firewall. Here we go. Xin Yan Kuai Le. That's pretty good. Very good. Okay. So.
That's it.
So we're done. We're out of here. No, actually, let's take a look at the homework that's due today. I realize some of you might have questions. So
That really depressing.
let's take a look at any of the problems from assignment 8.1 on which you may have had questions. The solutions are online. This is your chance to ask. Raise your hand if you're thinking you might be asking one or more questions during this session. Okay, so it looks like there's some questions here. So who'd like to go first? This is assignment 8.1. Max, do you have one?
Yeah, it's on 47.
All right, the question is on number 47. Let's take a peek at that one. Now, one of the things about number 47 is that, first of all, I can see it's an alternating series. The directions say, determine the convergence or divergence of the sequence with the given nth term. Now, there's a difference between whether or not a sequence converges and whether or not a series converges. Most of what we do in this unit will be about looking at a series and figuring out whether it converges or diverges. But this is just the sequence. And to answer that question, all you have to do is look at the formula for the nth term and take its limit as n approaches infinity. Now, notice that if it weren't for the alternating factor, -1 to the n is the alternating factor, because notice what happens. As n increases by 1, -1 to the 1, -1 squared, it goes positive, negative, positive, negative. If it weren't for the alternating factor, the limit as n approaches infinity would just be 1. This fraction, 99 over 100, 100 over 101 is getting closer and closer to 1. But the thing is, because it's alternating, each term in the sequence gets closer to 1, closer to -1, closer to 1, closer to -1. So it's approaching both 1 and -1. And so the point is that since it's not like it's diverging because it's going off to infinity, it's diverging because it's not converging to any particular number. It keeps oscillating back and forth between close to 1, close to -1. So that's why we say it diverges. Does that answer your question to your satisfaction? Okay, are there any other questions on the homework that was due today, assignment 8.1? Raise your hand if you're pretty sure that you do not have any additional questions. So it looks like, okay. Edward, do you have any questions? Maybe you can Skype in. Do they let you Skype over there?
Yeah.
You do?
Yeah.
That's a bonus. All right, so maybe we should let Edward ask some questions. Let's continue with where we left off yesterday. So remember what was going on yesterday. We were looking at the concept of a series and how it's distinct from the concept of a sequence. In my mind, one of the high points of the lesson was when we proved that the harmonic series counterintuitively diverges. Most of you had little voices inside that said, it converges, harmonic series converges. It's going to top out somewhere. But we found out that it really diverges. How did you know, by the way, or was it just a guess, that the harmonic series diverges? Do you remember yesterday?
Yeah, they had bad marks.
It keeps
The denominator is never going to be 0. It will always be something adding on the original thing.
Well, that's the same thing with 0.9 repeating,
Yeah.
is that you've got, 0.9 plus 0.09, you're always adding on something. You're adding on an infinite number of things, but that converges to 1. So yeah, it's not always easy to tell. The harmonic series is one of the hardest ones to figure out. But where we ended class yesterday was this idea that if you want to find the value S of a series, that's what we're going to learn or use for the whole unit is the symbol S. The value of a series can always be thought of as the limit, as n approaches infinity, of the nth partial sum. So as goes the sequence of partial sums, so goes the series. That was the message from yesterday. We didn't quite fill in this in the lower right-hand corner. For problem number 4, we wanted an expression for a sub n. And the nth term is actually expressed here. It's given in the problem as 2 to the n minus 1. The question is, what is the nth partial sum? And being able to come up with a formula for the nth partial sum is, oh, that's interesting. We did do it yesterday. So the nth term was 2 to the n minus 1, but the nth partial sum, we did come up with 2 to the n minus 1. We just didn't write it down in the blanks. And so that means if you take the limit as n approaches infinity of the nth partial sum, which is clearly going to infinity, that means that this series diverges to infinity. All right, now let's pick up then on the next page, picking up from yesterday. The definition of convergent and divergent series. We're going to look at 10 tests for a series being convergent or divergent. But then there's the definition that we want to look at separately. So, if the sequence of partial sums, sequence S sub n. So the pointy braces mean sequence, capital S sub n means the nth partial sum. If the sequence of partial sums converges to S, then series A sub n converges to S. This is just a fancy way of saying, as goes the sequence of partial sums, so goes the series. By the way, if the sequence of partial sums diverges, then series A sub n diverges. It's interesting that, you can ignore a finite number of terms in an infinite series. And if you do, ignore a finite number of terms in the infinite series, that does not affect divergence or convergence. Like, for example, take the harmonic series from yesterday, and let's toss out the first 1,000,001 terms. 1 plus a half, plus a third, plus a fourth. Let's throw them away. Let's toss out the first 1,000,001, and let's just start the series with 1 over 1,000,002, plus 1 over 1,000,003, plus ... forever. You might be wondering, how sensitive is this series to whether it converges or diverges? Does this series, the harmonic series, rely on its first 1,000,001 terms to catapult it over the wall and get into infinity territory? No, it doesn't need them. You can ignore the first 1,000,000. It's counterintuitive, isn't it? You can ignore a finite number of terms. Now, if you were to ignore every other term, that would be ignoring an infinite number of terms, and that would influence the convergence, or it could influence the convergence or divergence. But you can ignore a finite number of terms, and sometimes when you're working with series, it's very convenient to be able to ignore a few terms in order to get your processes to work more cleanly. And so it's okay, you can do that. You don't have to worry about ignoring a finite number of terms. It will influence the value of this series if in fact the series converges, but it will not affect whether or not the series converges. And so that's an important fact. So we're going to look at the nth term test and the geometric test. Those are T1, test 1, and test 2. Test 1 is the nth term test. Test 2 is the geometric series test. We've got to learn a total of 10 before next Friday, because the test is next Friday. So we're going to get, actually we get 5 of the test today, because assignment 8.2, which is due on Friday, covers tests 1 and 2. And assignment 8.3, which is also due on Friday, covers tests 3, 4, and 5. So we're going to get half of the 10 tests today. And it does occur to me that I don't think I've taken attendance yet. Should do that. People are watching, they're paying attention, whether or not I'm paying attention. Actually, got an email from my dad last night. He saw yesterday's lecture, he went on my YouTube channel and actually was, wow.
Wait, we're not all present.
I know, but what I do, I mark all present, and then I go in and modify things by taking attendance. So Edward, are you here? He appears to not be here yet. And then we've got three, we've got one. Looks like everyone else is here, so. All right. But yeah, my dad is almost 92 years old. He was a professor of physics. In fact, my dad taught calculus back at the University of Wichita. That was his first teaching job. So yeah.
What was on your first birthday cake?
Yeah, on my first birthday cake, yes. So because you're probably referring to the fact that my daughter's first birthday cake, daughter of a calculus teacher, had the definite integral from 0 to pi over 2 of sin x dx, which mine was, I think it was a candle. I think there was a candle on there, if I recall correctly. Yes, that's good. Good question. All right, here we go. Nth term test. This is the first of 10 tests for convergence or divergence. Here we go. The nth term test. If the sequence A sub n, does not converge to 0, then the series A sub n, that's sigma A sub n, you pronounce that series A sub n, diverges. Now, this is a bottom shelf concept. I mean, think about it. Suppose you have a series where the nth term is getting, not like what Rapunzel was talking about with a series that's, each term is getting closer and closer to 0. Like that's what happened with the harmonic series, 103, 104, 105. The nth term is getting closer and closer to 0, which is, I think, part of why it's so counterintuitive that it diverged. However, what if the nth term is getting closer and closer to 8? So it's like you're adding up an infinite number of 8s. This is not brain science to figure out that this thing's going to diverge. It's not even rocket surgery. This thing is going to diverge, okay? If you have a series that basically is an infinite number of 8s being added up, or any other real number that's not 0, then an infinite number of those non-zero numbers added up is going to take you off to divergent territory. This is a bottom shelf idea. It's not complicated. Okay? So, also, by the way, the series diverges if the limit does not exist. So if you're doing the nth term test and the limit comes out not to 8, so if it comes out to 8, 10, 12, maybe it comes out to infinity, well then you would also conclude that it diverges. By the way, if sequence A sub n does converge to 0, then there's no conclusion. You see, the nth term test is not sensitive enough to detect convergence. It's only sensitive enough to detect basic divergence. It cannot detect convergence. I'd like to show you how you're going to roll on these homework problems when you're checking to see if a series converges or whether it diverges using the nth term test, okay? So this gives you a feel for how quickly your homework is going to go on the 2 assignments that are due on Friday. All right, here we go. When you're using the nth term test, there's 10 tests, good grief. So you have to tell me the title of the test that you're using. Otherwise, I don't really know which one you're using. You don't have to write the word test, because as long as you underline it in this context, I know you're performing a test. So you write nth term, underline it, and then tell me what the formula for the nth term is. It's 1 over 2 to the n. It's series A sub n. And there's only one step. Some of these tests have 4 steps, but I want you to number your steps. And the nth term test has 1 step. You take the limit as n approaches infinity of A sub n. sometimes you have to replace a sub n with the expression and actually do some work. It might require that you use L'Hopital's rule or some other limit techniques. But in this case, come on, you can tell that the limit as n approaches infinity is equal to what, class?
0.
It's 0. Therefore, no conclusion. Whenever the nth term test gives you a limit as n approaches infinity, if the nth term is 0, then you're done. There's no conclusion. We just don't know. We're going to have to use one of the other tests for convergence that's more sensitive in order to figure it out. However, if you take a look at number 2, let's perform the nth term test. So write nth term, underline it. The nth term formula is 3n plus 5 over 2n minus 100. Step 1, 1 of 1. The limit as n approaches infinity of a sub n. This time, you can do it in your head. I mean, technically, it's in the form infinity over infinity, so you could use L'Hopital's rule. Come on, don't use L'Hopital's rule. This is just one of those pre-calculus advanced problems where you can tell, since it's degree 1 over degree 1, it's balanced. The limit has to be what, class?
0 and 2.
So 3/2. 3/2. Now, since it's always either equal to 0 or not equal to 0. Those would be the two results, and 3/2, or diverges, in which case you would say the series diverges. But since that's in the does not equal to 0 category, that's what you have to know. So you're not checking to see is it greater than 1, less than 1. You're checking to see is it in the does not equal to 0 category or not. Since it is not equal to 0, we can draw a conclusion. And our conclusion is 3 dots in a triangle, therefore sigma a sub n diverges. What do you mean by a sub n? Well, we defined a sub n up here. We know what a sub n is. So every time when you use a test for convergence or divergence, you're going to define your symbols up front, and then you're going to start your steps. Now, I want you to try number 3 on your own. Perform the nth term test and come up with either diverges or no conclusion. So when you took the limit as n approaches infinity of the nth term, what did you come out with on that one? Kennedy?
I got that the limit as n approaches infinity is 1.
Yeah, I agree. 1 is correct, because you have degree 1 upstairs. Downstairs, half of 2 is 1. Degree 1 over degree 1, the ratio of lead coefficients is 1. So into which category should I place the limit of 1? Gwyneth?
Not equal to 0.
Yeah, it does not equal 0. Categories are going to be the most challenging part, remembering the 10 categories. Okay, each test has its own category. And here it's either equal to 0, no conclusion, does not equal to 0, and diverges will be, therefore, series a sub n does what, class? Converges or diverges? Diverges, because this is essentially like adding up an infinite number of numbers that are really close to 1. It's going to diverge to infinity. Any questions on this one? All right, number 4. So let's roll through the nth term test on this one. Nth term, in this case, a sub n is equal to 5 to the n plus 3 over 5 to the n plus 2. Now, keep in mind that 5 to the n plus 3 over 5 to the n plus 2 is, step 1, something that we should rewrite. The limit as n approaches infinity of a sub n is going to be the limit as n approaches infinity. This time I'm going to write down what a sub n is in a different form. It's numerator of 5 to the n plus 3. For the denominator, I'm going to write 5 squared times 5 to the n, which is 25 times 5 to the n. You see, I broke the 5 to the n plus 2 in 5 to the n times 5 to the 2. 5 squared is 25. So now I've got degree n over degree n, and the ratio of lead coefficients is 1/25. So the limit is 1 over 25, which is in the does not equal to 0 category. Therefore, we wrap things up by saying, therefore, series A sub n diverges. Do you have any questions on that one? All right, so it doesn't have to be a fraction. Let's look at the shortcomings of the nth term test. Notice how if we take the harmonic series, which just boggled your minds yesterday, look at what happens when you take the nth term test to the harmonic series. So we write nth term underline. Define a sub n as 1 over n. We do our one and only step. We take the limit as n approaches infinity of a sub n, which is 1 over n, which is 0. That limit is 0. Notice, even though it diverges, we know the harmonic series diverges from yesterday's proof. We do not arrive at that conclusion using the nth term test. The nth term test is not sensitive enough to detect these non-obvious cases of divergence. So when you get 0, the nth term test tells you you don't have a conclusion. You're going to have to use one of the other tests to prove that the harmonic series diverges, because honestly, on the AP test, you're not going to want to have to do some sort of proof like this, some highly involved proof where you're drawing diagrams and making arguments. No, you want a very elegant, efficient way of detecting whether or not a series converges or diverges. So it's important to note that the nth term test is not very sensitive. Also, summation from n equals 1 to infinity of n. We're talking 1 plus 2 plus 3 plus ... forever. This is an example of a situation where the nth term test, where a sub n is n, gives you 1. The limit as n approaches infinity of n diverges. What's the conclusion about series a sub n? Therefore, series a sub n does what when the limit diverges? Class? It says it right here, this kind of footnote thing. Also, the series diverges if the limit does not exist. The limit as n approaches infinity of n does not exist. Therefore, series a sub n diverges. And try running the nth term test in your head. Look at 1 over n squared. What's the nth term test going to give you on this one? Diverges or no conclusion? Yeah, so get used to doing these mental tests, because sometimes you have to run through them in your mind. You know, nth term test, oh, that'll be no conclusion, so then you'll move on. You don't have to write it down to run it through in your mind. Do you have any questions on the nth term test? All right, so that's test 1, the nth term test. 1 down, 9 to go. But today it's 1 down, 4 to go. We got 1 more hour. Okay, now let's go to geometric series. Geometric series either converge or diverge every time. Every series either converges or diverges, whether we can conclude that or not. So I don't know how long it's been since you've looked at geometric series, but let's just get familiar with the pre-calculus of geometric series, and then we'll go to the calculus of geometric series. So first of all, summation from n equals 3 to infinity of 3 times 1/2 to the n. Now, it is important to know, there's probably a lot of you have that formula in your mind that if you have an infinite geometric series, that you take the first term, if you let A roughly represent the first term over 1 minus r, that's the value of the series. The series will converge to that, provided a condition is met. What is the provision that has to be met before you use this formula? Does anyone happen to recall from pre-calculus? You're saying you don't remember? For sure you don't remember? This, we'll find out, we'll get a feel for why this is the case, but it's only when the absolute value of r is less than 1 that you're entitled, permitted actually, to use this formula. The common ratio has to have an absolute value less than 1 in order to do that. How many of you recall in pre-calculus finding the value of an infinite series by taking first term over 1 minus r whenever the absolute value of r was less than 1? Let me just see how much familiarity people, it looks like some of you remember doing something like that in the past. Let's take a look. Now, we're taking the summation from n equals 3. The first value of the index of summation is 3. So the first term is going to be 3 times 1/2 cubed. The second term is 3 times 1/2 to the 4th. Keeps on going forever. And so the first term is actually this whole thing. It's 3/8. So A, the first term, put this in the margin, is 3/8, and the common ratio is 1/2. So if you did want to find the value of this series, you would just take 3/8 equals 3/8 over 1 minus 1/2. That's 3/8 divided by 1/2, or 6/8. So that series converges to 3/4. You didn't even have to do a test for convergence. You just found out that it converged to 3/4. Try number 2 on your own. See if you can figure out what's the first term and what's the common ratio for the summation from n equals 0 to infinity of 8 times 3/4 to the n. Okay. Well, put a 0 in front. First term is 8. Common ratio is the base of the exponential expression. So these are kind of easy to spot when the number subtracted from the exponent matches the first value of the index of summation. See, n minus 0 and 0. In number 1, it didn't match up. This was n minus 0, and the first value of the index of summation was 3. When those don't match, you actually have to substitute the first value of the index of summation. By the way, the index of summation is whatever variable happens to be beneath the sigma. And yeah, so it wasn't a matter of just taking 3. There's a lot of people who mess up on problem 1, and they'll say a is equal to 3, first term is 3, common ratio is 1/2. They'll take 3 over 1 minus 1/2. That's a mistake. But here, it's just going to be 8 over 1 minus 3/4. Pre-calculus, 8 over 1/4 is 32. So that series converges to 32, therefore it converges. Now, in general, you've got the summation from n equals c to infinity of a times r to the n minus b. And so in that situation, what we're talking about is it converges to s equals, I'm just going to skip to the value. The first term is found by putting the c in for n. So the first term is it's basically a over 1 minus r. All you got to do is focus on this, and that's provided that c is equal to b, and provided that the absolute value of r is less than 1. So if c and b are the same number, then all you have to do is take a over 1 minus r. Just check to make sure the absolute value of r is less than 1. So take a look at, do we have an equivalence? Do we have c equaling b? Let's find out. N is n minus 0. Here they don't match up. So it would be a mistake to take 8 over 1 minus 3/4. Instead, what is the first term in problem 4? Class? Go ahead and call it out. It's 6. It's 3/4 of 8. R is 3/4. So go ahead and find the value to which the geometric series converges in problem 4. When you're done, take a look up here at the screen. Hopefully you came up with 24, and then try number 5 also on your own. You're just getting familiar with infinite series, particular species of infinite series called geometric series. Yep. Okay, so the first term found by putting a 3 in for n is 8 times 3/4 to the 4th. Now, 8 times 3/4 to the 4th over 1 minus 3/4. So we could take some time to simplify 8 times 3/4 to the 4th. 1 minus 3/4 is 1/4, but to whatever number that simplifies, that would be the answer. Now, keep in mind that had any of these fractions been like, 2 instead of 1/2, 4/3 instead of 3/4, we would have said, oh, we're not meeting the absolute value of r is less than 1 condition, and therefore the series diverges. We cannot use the first term over 1 minus r formula. All right, now let's go to the geometric series test. Test T2. Now, suppose we have the geometric series sigma a times r to the n. That's a pretty stringent requirement for using geometric series. For the nth term test, geometric series test, for the nth term test, the only requirement that we had to go forward with the test is that it just had to be a series. All we needed was a series in the form sigma A sub n. That's every series. Okay, you can apply the nth term test to every series. But notice that for the geometric series test, you have no business applying the test unless your series is in the form constant times r to the nth. Okay, here we go. If the absolute value of r is in one category, then the series converges. If the absolute value of r is in another category, then the series diverges. So this test is sensitive enough to detect both convergence and divergence. What's the category? Well, if the absolute value of r is less than 1, it can't be equal to 1. So if you're taking, let's say you have 5 times 1 is 5 times 1 is 5. If you keep multiplying by 1 every time, you're adding up an infinite number of 5s, or an infinite number of whatever the first term is. And so r can't be equal to 1. The absolute value of r has got to be less than 1, then it will converge. If the absolute value of r is greater than or equal to 1, then it diverges. So think of the categories that you have to keep straight in your mind. For the nth term test, your categories are either equal to 0, it's either does not equal to 0. That's what you're hoping for. You're hoping that your limit will come into the category of does not equal 0, in which case you can say, yay, it diverges. If the limit is equal to 0, then you're stuck. You get no conclusion. So it's either does not equal to 0 or equal to 0. Those are the categories. Here, it's either less than 1 or greater than or equal to 1. Let's see how we actually document these. So let's do let's do what I expect you to do, and that is every time you get to a question where they say, oh, by the way, circle both divergence and convergence, but if they say, determine whether or not this series converges or diverges, in your mind, you need to go through all 10 of the tests, which means you start with the nth term test. Okay, nth term test. If you did the nth term test on problem 1, even though it's a geometric series, if you did the nth term test with a sub n is 5/3 to the n, and you did step 1, which is take the limit as n approaches infinity of a sub n, what would that limit do? Would it converge to a number or would it diverge? Scott? What happens when you take the limit as n approaches infinity of 5/3 to the n?
The limit wouldn't exist, so it diverges.
Yeah, this would be dne, does not exist. Therefore, sigma a sub n diverges. So if you use the nth term test, even though this is a geometric series, it would give you it would give you divergence. However, notice a very similar series number 2. Run through the nth term test in your head. Would you get a conclusion or no conclusion on this? You see, take 3/5 to the end. 3/5 to the first, take 3/5 of that, 3/5 of that. When you keep taking 3/5 of things, you eventually get to what number, class? Yeah, you get to 0. 3/5 to the end, just like 1/n goes to 0. The limit as n approaches infinity of 3/5 to the n is 0. So nth term test would give you no conclusion here. Let's go back to this first one. What if instead of the nth term test, even though it would work, what if we used the geo series test? So if you're going to use a geometric series test, announce that to me by writing geo series and underlining it. Here's your first example of documenting the geometric series test. 2 definitions up front. First definition, tell me what you think R is. In this case, R is 5/3. Second, comma, tell me what you think A sub n is. In this case, the nth term formula is whatever's inside the sigma, 5/3 to the n. Okay, so you defined your symbols. Now, geometric series test also has only one step. And that step is to consider the absolute value of R. Absolute value of R, which in this case is the absolute value of 5/3. Absolute value of R is 5/3. Into which category should I place 5/3? Should I put it into the does not equal to 0 category? No, I mean, it's true that 5/3 does not equal 0, but that's categories used for the nth term test. We're in the geometric series test, and our categories are either less than 1 or greater than or equal to 1. So we put it into the greater than or equal to 1 category. Therefore, sigma A sub n diverges. So we got the same result, series A sub n diverges, using both the nth term test and the geometric series test. Doesn't matter which one you use, as long as you use the test correctly. Any questions on that one? All right, now let's use, since nth term test gives you no conclusion for this problem over here, problem 2, let's use the geometric series test, where R is 3/5, comma, A sub n is the quantity 3/5 to the n. What would the first step be? What should I write down for this, starting with William? William, what's the first thing I write down?
Absolute value of R.
Absolute value of R equals, what's the second thing we write down? Help me out, please. Max Martin. Close. Absolute value of 3/5. And then write 3/5. Then simplify it, okay? And then into which category do I place that? Ethan. Yeah, your geometric series categories are either less than 1 or greater than or equal to 1, so you're correct to say it goes in the less than 1 category. What's my therefore statement then? Therefore what? Help me out, please. Jenny. Say, series A sub n converges is correct. It's very good. Okay, class, I'd like you to do problem 3 on your own. I'm going to tour the room. And just FYI, nth term test would give you no conclusion. So cross that off your list. Do nth term test in your head, no conclusion. Now do the geometric series test for problem 3. Here I come. See if you're actually talking to this. All right, notice it doesn't matter what the first term is. For step 1, all you need to say is the absolute value of R is the absolute value of negative 3/4, which is 3/4. That's in the less than 1 category, therefore series A sub n converges. See how quickly these go? I mean, bam, they're done. Any questions on how to do problem 3? Class, what's going to happen in problem 4? Just run the geometric series test in your head. It's going to come out to what? Raise your hand if you think you know what the conclusion for geometric series is going to be on problem 4. Moose?
What?
What's going to happen on problem 4 when you run the geometric series test?
Absolute value of R will be 3/2.
Which is in which category?
Greater than 1.
No, it's the greater than or equal to 1 category.
Yeah.
Because sometimes you'll get 1. You got to know your categories. It's less than 1 or greater than or equal. That's what you're learning today. We're not learning the fundamental theorem of calculus, not learning how to evaluate improper integrals. You just need to know your categories. Get a stranglehold on your categories. So that's going to come out to be divergence. How about number 5? Number 5, this is one of those situations where they don't give you the sigma notation. I'm just going to pull that up, 9/2, 27/8. So problem 5, just giving myself a little more space. Problem 5 is 8 plus 6 plus 9/2 plus 27/8. In order to make this problem happen, I just want to make sure I got the signs. Is it alternating? Is it, no, it's on, you know what? Yeah, that's fine. So it's not alternating. Here's what I would expect you to do if they don't give you sigma notation. Put little carets above each pair of terms and divide. Second term divided by the first term is 3/4. I wonder if that's really the common ratio. Let's see, what's 9/2 divided by 6? Or 9/2 times 1/6? Well, that comes out to be 3/4 also. It looks as though if I multiply 9/2 by 3/4, does that in fact give me 27/8? I've discovered the common ratio. So you are expected to be able to take a geometric series that's in ellipsis form and convert it to sigma form. I would expect you to say that this series, we can call it S. It's an infinite series. S can also be written as the summation from, and we usually just start from n equals 0 to infinity. You could start from 1, but n equals 0 to infinity of 8 times the common ratio 3/4 to the n. Now, would you be okay if I said it's the same as the summation from n equals 5 to infinity of 8 times 3/4 to the n minus 5? Is that an accurate alternate way of writing this series? Same thing. Both of these series have a first term of 8 and a common ratio of 3/4, so we're okay on either one. Once you've converted the series from ellipsis form to sigma form, then you can go ahead and document your application of the geometric series test. Go ahead and in the lower right-hand corner there, hopefully you have enough room to document your use of the geometric series test. Go ahead and perform the geometric series test.
There.
Okay, so it's a convergent geometric series. Any questions on that one? Lower right-hand corner, number 6, IOC, that's an acronym for interval of convergence. Let's find the interval of convergence for this one. The interval of convergence is basically a set of x values that cause r to have an absolute value that's less than 1. Because this series is in geometric form. A times r dn. Now, actually the first term is not 3, 5, or 8 because we don't have a match between 2 and 3. But the interval of convergence is found by saying, I want to find all the values of x that cause the absolute value of r to be less than 1. So let's write down our starting point whenever you're asked to find the interval of convergence of a geometric series. In this case, r is 8x over 3. So we have to solve this inequality for x. It's an absolute value inequality that's in the less than format, so you can put it in 3-part form. You can say -1 is less than 8x over 3 is less than 1. Dividing all 3 parts, multiplying all 3 parts by 3 and dividing all 3 parts by 8 gives you -3/8 to 3/8. The interval of convergence is x is an element of the set. Parentheses, this is an open interval, -3/8, comma, 3/8. The parentheses indicate the open interval. Had I used square brackets, that would have been closed interval. So it's the open interval from -3/8 to 3/8. As long as x is one of those numbers, this series will converge to first term over 1 minus common ratio. Otherwise, it will diverge. Do you have any follow-up questions on that one? On the next page, we're going to look at home screen programs, which we explored yesterday. But this is just learning how to debug home screen programs, because not everyone writes these things correctly. We already did a home screen program for this guy. We wrote it yesterday, and it's here. As long as you initialize n at 0, you should always initialize n at the number that is 1 less than the initial value of the index of summation. Because the very first thing that happens in this program, like check out what would happen if you did 1 store n and then n plus 1 store n colon 1 over n store t colon n comma t display. If you did this, I sometimes use a table to analyze these programs. If n is 1, or if 1 is stored in for n, 1 is assigned to n, then the first thing the program does is it bumps the value of n up by 1 to 2, and then 1 over n, or 1/2, is stored in for t, and it displays 2 comma 1/2. That is not the first ordered pair. The first ordered pair is 1 comma 1. The first term is 1, not 1/2. So that's why we had to debug it and initialize it at there. Now, if you're doing the summation from n equals 0 to infinity, let's say 1 over n plus 5, if this is what you're trying to work on, then you would initialize n at -1. So you do -1 store n, because -1 is 1 less than 0, and then go to n plus 1 store n colon 1 over the quantity n plus 5 store t colon, and then display the ordered pair. So, correct program for the first 10 terms is that one. Okay. First 10 partial sums, this is what we did in class yesterday. The last page of this handout, let me check, is just, oh yeah, that's a website we're going to be using later on, but that completes the lesson. You now know how to do assignment 8.2, which is due on Friday. The other assignment that's due on Friday is assignment 8.3. If you want paper notes, come and get them. And otherwise, go to the 8.3 PDF document on Academy Central. Let's begin. The next 3 tests for convergence or divergence. All right, notice that the first page of this handout is a summary of the first 5 tests. There's only 10 of them, and here's the first 5. Now, notice that this is like a quiz to see if you remember any of the things I've taught you. By the way, the first test is the nth term test. To qualify for the nth term test, the series needs no special qualifications. It just needs to be series A sub n. So it's easy to qualify for the nth term test. Every series qualifies for the nth term test. If Blinkham, it never converges, so X that one out. The only thing we have here is if the, step 1, if the limit as n approaches infinity of A sub n, see if you remember what it was, no notes. It diverges if what? If the limit as n approaches infinity of A sub n does what, class? Does not equal 0, and footnote, or if the limit does not exist. Let's say, or limit dne. So there's 2 ways to get divergence. And by the way, comment, if lim equals 0, then no conclusion. So that's just a review of the concept of the nth term test. Let's review the concept of the geometric series test. To qualify for the geometric series test, you got to be in the form a times r to the n minus c to n equals b. Okay, so it converges if the absolute value of r is less than 1, diverges if the absolute value of r is greater than or equal to 1. And by the way, a comment is that the value of the series, in case they actually want you to report out the value of the series, just take the first term, which is, so a over 1 minus r, provided, there's 2 provisions here, provided c is equal to b, and what's the other provision? Max? So was that my? No, the absolute value of r has got to be less than 1.
Oh, yeah.
Which, that's true, if r is equal to 1, then the absolute value of r is not less than 1. But the main thing is that the absolute value of r has to be less than 1, which is a stronger, it's a stricter restriction provision than simply r cannot equal 1. Okay, so that's what we've learned so far. That wasn't too bad, right? 2 tests are pretty understandable. Now, 3 more today. The telescoping series test is hardly ever used because there's hardly there's a lot of telescoping series, but the probability that a randomly selected telescoping series will satisfy this condition is 0. It does happen, but the probability calculation comes out to 0 because it's finite over infinite, okay? So, or it may be infinite over infinite, but it's not gonna happen. So, it's not gonna happen to the extent that it'll change the probability to other than 0. But there are things that happen where the probability of that happening is 0. That's a little surprising. But if you happen to get a telescoping series that does satisfy this condition, which probably won't happen to you on the AP test, but just so you know, it'll show up on the test in this class. There's one step to this test, just like there was one step up here. Yep. Let's put down the number of steps. So if the limit as n approaches infinity of a sub n plus 1, you can see it's the general representation here of the nth term is if it's in the form a sub n minus a sub n plus 1. If the limit as n approaches infinity of a sub n plus 1 equals L, comma, a real number. It's okay if it's 0, it just can't be infinity. Can't be, does not exist. If it comes out to L, a real number, then it converges. If, however, the following condition is met, then the telescoping series diverges. If the limit as n approaches infinity of a sub n plus 1 does not exist, then the telescoping series diverges. By the way, the value of the series is a sub 1 minus capital L. First term, a sub 1, not the first pair of terms, just the first term minus whatever this limit is. So that's a nice to know but not need to know. P series. P series, something that we foreshadowed back when we were evaluating improper integrals. We did the integral from 1 to infinity of 1 over n squared, 1 over the square root of n. We did all sorts of different values of p. And so, having done that experience, do you remember what values of p when you integrated from 1 to infinity? Which values of p caused the series to converge? We did it in class. It was reinforced on the homework. What did p have to be in order for the definite integral to converge? Moose? Jessica got it. It had to be greater than 1. That was all designed to prepare you for the P-series test, which is happening now. There's only one step in the P-series test, and that is if P is greater than 1, then it converges. If P is less than or equal to 1, then the series diverges. So you kind of already learned that one. And then the final test for today, the integral test, has 4 steps. Steps 1, 2, 3, and 4. All right. Now notice the qualifications for using the integral test. There's none, as long as it's a series. As long as it's a series, you can use the integral test. Compare that to the P-series test. There's very few series that fit into this category of a P-series. But there are 4 steps to the integral test. Step 1. A sub n has to be greater than 0. It has to be all positive terms. Now, what if it's like got 3 negative terms at the beginning and then all the rest are positive? Then throw away the first 3 terms, because if you discard a finite number of terms from an infinite series, it won't affect it. So if not all the terms are positive, but there's a finite number that are negative, just throw them away. And then you can still say the nth term is greater than 0. Okay, second condition. A sub n is decreasing. Third condition, A sub n is continuous. And then the fourth condition, the integral from 1 to infinity of A sub n dn converges. If all four of those conditions are met, then the series converges. If the integral converges, the series converges. Now, to show divergence, first three are the same. The nth term has to be positive. The nth term, basically a sub n has to be a decreasing function, or its first derivative has to be negative. But don't worry, you won't have to take first derivatives on that. You'll just be able to look at it and tell that it's decreasing. A sub n is continuous. If there's a discontinuity at n equals 5, then you can just toss out the first 5 terms and just start at 6 then. It's okay to toss out a finite number of terms if you want to make this work. If you really want to use the integral test, you can toss out a finite number of terms to make it happen. And then number 4, the integral from 1 to infinity, an improper integral from 1 to infinity of a sub n dn diverges. If the integral diverges, then the series diverges. I have a mnemonic device for remembering these conditions. You'll need to remember them. Positive, decreasing, continuous. The way that I remember positive, decreasing, continuous is I think of, back in Wisconsin, where my dad still lives and where I grew up, we had these stores called PDQ. It's like they're like on 2 or 3 in every town. In Waukesha, Wisconsin, where I grew up, there were like 3 or 4 PDQs back then. I don't know, there may only be one now. I'm not sure exactly what PDQ stands for, but I think it might stand for something like pretty darn quick. PDQ, pretty darn quick. It's a convenience store. You go in there, PDQ, something like that. I'm not sure exactly, something like that. So I just do a little variation on that. I just think pretty darn convenient is what I'm thinking. Those PDQs, those are pretty darn convenient. Positive, decreasing, continuous. PDQ. PDQs, they're pretty darn convenient. Positive, decreasing, continuous. When I say go, I'd like all of you to say out loud and in unison, belt it out. Let them hear you on the other side of the Great Firewall. Okay, let them hear you. When I say go, I'd like you to say, PDQ is pretty darn, say this. Say PDQ is positive, decreasing, continuous. Ready? Go. PDQ is positive, decreasing, continuous. Now, you might want to store it in your mind as PDQ is pretty darn convenient. And then that might, in your mind, then just step right over to positive, decreasing, continuous. So let's do an example of all of these. First of all, the telescoping series test. Let's take a look at problem 1. By the way, telescoping series is sensitive enough. It's sensitive enough to detect both divergence and convergence. Now, I have a series here. It happens to be a series that raises the question of, does this series match the qualifications for the telescoping series test? Is it in the form a sub n minus a sub n plus 1? Well, to figure that out, you'd have to say, if you're going to do telescoping series for this, you'd say, well, here's what my a sub n is. My a sub n is going to be this first term. And my a sub n plus 1 is going to have to be, I don't know if that fits it, but it's got to be n plus 1 quantity squared plus 6. So I've got to do a little bit of math to figure out whether or not the second term is an a sub n plus 1. So check it out. Expand it, you get n squared plus 2n plus 1 plus 6, which is n squared plus 2n plus, off by 1. You see how hard it is to meet this qualification? OBO, off by 1. So that's what we say.
Who says?
The OBO error, OBO, off by 1. We in the community of it's a sub-community of math educators, of which I am a member.
Who is the other member?
You want a complete membership list? You have to come back Friday for that. Okay. Now, class, it just doesn't match it. So technically you can't use the telescoping series test. Half the time what we do with telescoping series is we just see if we can try to find a pattern and see if it converges. Because if it converges to 12, then we say, oh, look, The series converges to 12. Therefore, the series converges. Let's go to the next page. Let's do this one, this example. Let's see what kind of series it is. By the way, in your head, you're thinking nth term test, right? Nth term, by the way, what does nth term test give you? A conclusion or no conclusion? Run it quickly in your mind. N approaches infinity, comes out to what? Friends, limit is what? Zero. Conclusion or no conclusion? No conclusion. So the nth term test is worthless here. Let's just take a look at this. In fact, actually, I see in my notes here that I wanted to, for the sake of time, we've got only 22 minutes left. I want to skip down to number 3. This will be a little more interesting. Notice how, if you were to try to use the telescoping series test here, and it's not going to qualify, but suppose you said, oh, it kind of looks like a telescoping series. Telescoping, underline, first term a sub n is 1 over n, and a sub n plus 1 equals 1 over n plus 1. Oh, rats, we don't have 1, we have 1 over n plus 3, so technically it doesn't qualify. But you can still deal with it, because watch what happens with this. So, okay, you can't use the telescoping series test, because technically it doesn't qualify. But what can we do? We can write out pairs of terms and look for the kth partial sum. We're going to find out what the kth partial sum is by writing out pairs of terms. Like when n equals 1, you got 1 minus 1/4. That's the pair of terms that you get when n equals 1. Plus, sigma means plus. So now let n equal 2. When n equals 2, you got 1/2 minus 1/5. 1/2 minus 1/5. When n equals 2 plus, what's the third pair going to be? Help me out, please, Max Martin. That's okay, you can just look up here. Let the value of the index of summation equal 3, in which case the...
1/3 minus 1/6.
Yeah, 1/3 minus 1/6. Write kind of tiny. I'm going to write a little bit smaller here too. Okay. Let's do another pair. I want to do 5 pairs before we go ... So before the ellipsis goes in, the fourth pair is going to be plus 1/4 minus 1/7 plus 1/5 minus 1/8 plus ... plus. Now, watch what's happening here. The reason we call it a telescoping series is that many pairs of terms collapse to 0. Like, watch this. Minus 1/4 plus 1/4 collapses or telescopes down to 0. Minus 1/5 plus 1/5 minus 1/6. There will be a plus 1/6 in the next one. Minus 1/7 is going to collapse down to 0 or telescope to 0 with plus 1/7. It turns out that if you take inventory of the terms that survive the telescoping process, we've got 1 is going to survive, 1/2 and 1/3. All the other terms are going to pair up with opposite terms and go to 0. It's actually easy to predict, friends, that there's going to be 3 surviving terms because the difference between the denominators is 3. Okay, so the 3 firsts, for the first 3 pairs, the first number in those first 3 pairs are going to survive the telescoping process. Now let's go to the last 3 pairs. It goes on forever, it goes to infinity, but let's write down the kth pair, the one before it, the k minus 1 pair, and the one before it, the k minus 2th pair. Okay, let's write the last 3, and but it will go plus ... from there. So check this out. When we get to n equals k, and I've run out of space here, so I'm going to steal some of the space from down here. So when we get to n equals k, that pair will be 1 over k minus 1 over k plus 3. Working backwards, the k minus 1 pair, the pair before that is going to be 1 over k minus 1 minus 1 over k plus 2. Just replacing both n's with k minus, that should be a k minus 1. N equals k minus 1. The term before it is the k minus 2th pair, replacing both n's with k minus 2. It's 1 over k minus 2 minus 1 over k plus 1. Now, the way this pattern is going to continue is, you see how the second number in the pair comes and snags the first number in the fourth pair? The second number in the first pair came and snagged the first number in the fourth pair, and they collapsed to zero. So we're going to have terms plus dot, dot, dot. So, and this, by the way, is plus dot, dot, dot on both sides. It goes on forever, but let's just analyze the kth term. You're going to have terms that were before, they come and they snag the first one. So it's going to come and snag this one. Something's going to come and snag the first term here. Something's going to come and snag that one. So there's going to be 3 surviving terms if you're going to look for the kth partial sum. And that is what we're doing. We're trying to find S sub k. The kth partial sum is basically a whole bunch of zeros. It all collapses down to 0, except for 1 plus 1/2 plus 1/3, which are the first 3 terms surviving at the front end. And then there's going to be 3 terms surviving at the back end, which are, oh, I wrote S sub k, it is S sub k, but it's also, it's a kth partial sum. So S sub k is equal to that. The 3 terms that survive at the back end, I'm going to highlight those, are going to be 1 over k plus 3, 1 over k plus 2, and 1 over k, actually minus 1 over k plus 3. So the kth partial sum is going to have a total of 6 terms. 1 plus 1/2 plus 1/3, and then minus 1 over k plus 1, minus 1 over k plus 2, minus 1 over k plus 3. Now, if you were to take the limit as k approaches infinity, because I'm arguing that S is the limit as k approaches infinity of the kth partial sum. That's why we care about finding the kth partial sum. We want to take its limit as k approaches infinity. The kth partial sum is basically 1 plus 1/2 plus 1/3 plus 3 zeros. These last 3 terms go to 0 as k goes to infinity. So really, the value of this telescoping series is 6, 6 plus 3, 6 plus 2, 6, 6. It's 11 sets. It's just 11 sets. And since 11 6, since the series converges to 11 6, therefore series 1 over n minus 1 over n plus 3 converges. It's not one of the 10 tests. I didn't use the alternating series test. The series didn't qualify for that, but I just found the value of the series. Now, because, similar thing here in number 4, because the difference between the denominators is what it is, how many terms do you expect there to be in the value of the series, class? Expect there to be 4 terms. And so really all you have to do is write out the first 4 pairs, figure out what it is. When you put a 5 in for n, the first pair, we'll call it the n equals 5 pair, is 2/5 minus 3 over 1. Plus, write out the n equals 6, n equals 7, and n equals 8 terms. Yeah. This one actually has a slightly unexpected feature to it. But yeah, we'll see this in a second. 2/8 minus 3/4. Okay, I wrote out the n equals 5 term, n equals 6, n equals 7, n equals 8, n equals 9. You have to actually look at these things because some of them surprise you. Like for example, it's not as simple as the previous one where both of the numerators were 1. This one's a little bit different. We see a 2/5 up front here, and the next time we get a denominator of 5 is negative 3/5 way over here. 2/5 and -3/5. They don't collapse to 0, they collapse to -1/5. Now, let's go to a different color. Let's go to red. 2/6. 2/6 collapses with, no, I don't want to go with 2/6. I want to go with 2, well, maybe I do. Yeah, I do want to go with 2/6. 2/6, even though I didn't write it down, do you agree that there will be, in this next pair that I haven't written down yet, there will be a -3/6? We didn't write it down, but you can anticipate it will be a -3/6. So the blue pair adds to -1/5. The red pair adds to -1/6. And then there's going to be, the next pair is going to, that's the patterns, -1/5 plus -1/6 plus -1/7, etc. Yeah, there are 4 surviving terms up front, but here's what needs to be said about what's happening. This series basically is these first 4 terms, we'll call it, A1 plus A2 plus A3 plus A4. I don't know what they are, but then we get plus -1/5 plus -1/6 plus -1/7 plus ... forever. And the question is, what is that thing? You saw it yesterday. This is basically some number. These first 4 terms add up to something, plus negative summation from n equals 5 to infinity of 1 over n. It's the harmonic series with a negative sign out front of it. It's not the entire harmonic series. We're ditching, we're flushing away, we're throwing away the first 4 terms of the harmonic series. The point is, what does the harmonic series do, class? It diverges, and therefore it's a number plus diverges. This series, sigma a sub n, diverges. So you never know for sure what's going to happen. You have to look at the pattern every time when you see a telescoping series. Sometimes it'll converge to a predictable number of terms, sometimes it'll diverge. But this is a nice connection with the harmonic series. Next. The next page is actually a pre-calculus review problem, which I don't want to hit unless we have time at the end. There's no calculus required for this problem. Instead, I want to make sure you get p-series and integral test. It's optional, depending on. So now go to the page that says p-series. Let's, for the first time, practice using the p-series test, which is, notice how we never really did a telescoping series test where it satisfied the qualifications for telescoping series. That's because it hardly ever happens. And if you need to do it, it'll be in the homework solutions. Now, here we go. P-series. These fly. This is the shortest of all. In a p-series test, define your a sub n, it's 1 over the square root of n. Write it as n to the 1/2. Rewrite 1 over the square root of n as 1 over n to the 1/2. Right, here we go. Step 1. There's always only one step in p-series. P equals 1/2. Got to get your categories straight. What are your p-series categories? Less than or equal to 1. Remember, if it's equal to 1, harmonic series is a p-series with p equals 1. Harmonic series is a p-series where p is equal to 1. So you know that's got to diverge. Okay? So your categories are not, it's not less than 1. Like it was for geometric series, it was less than 1. In p-series, it's less than or equal to 1. And since 1/2 is in the less than or equal to 1 category, we say, I'm going to pull this down a little bit. Now I have room to say, therefore, 3 dots. Therefore, sigma a sub n does what, class? Diverges is correct. So, p-series. Try the next 3 on your own. Try those 3. P-series goes fast. When you're done, look up here, see if you got it. Yep, there it is, harmonic series. You don't have to use some fancy proof. It's just a p-series. P is equal to 1, which is in the less than or equal to 1 category, therefore series a sub n diverges. Told you these would go fast. Okay, so we got an example here where step 1, p is 10/3, or 10/9, put 10/9 into the greater than 1 category, therefore series A sub n converges. Any questions on that first example, which was really 4 examples? All right, moving right along. We're gonna get this. Next, by the way, sometimes they don't give you the series in sigma form, sometimes it's in ellipsis form, so you just have to convert it. Summation from n equals 1 to infinity. What's the pattern here? Let's say n squared. It's 1 over n squared. Hey, that's a p series, so let's document. We write p series where the n term is 1 over n squared. Step 1. What's the value of p in this situation, class? 2. Into what category should I place 2? Jessica? It's in the greater than 1 category, therefore series A sub n converges. So good job on that one. Now, sometimes the symbols get all mixed up. Is it even a p series in the first place? Now, keep in mind, 1 over e to the n. It's got to be, what is a p series? It's 1 over n to the p, not 1 over e to the n. This is not a p series. It looks like a p series, but it's meant to confuse you. So keep in mind, by the way, what test would we use in your head? Let's go. First test is nth term. Nth term test, 0, no conclusion. Geometric series. This is a geometric series. Check this out. It's the summation from n equals 1 to infinity of 1 times an eth to the n. Isn't that the same thing? 1 over e to the n. But now that we've shoehorned this into the form a times r to the n, it's going to be geoseries. And this is going to be, a sub n is equal to this. Just the quick version of this. Absolute value of r is the absolute value of 1 over e. 1 over e, 1 over 2.7, Andrew Jackson, isosceles right triangle is in the less than 1 category. Therefore, series A sub n is a convergent geometric series. Series A sub n converges. Okay, so can't use p series here. A lot of these things look like p series, but they're not. How about this second series right here, 1 over n to the pi? Is that a p series, class? Yeah, it is a p series. Well, is it a convergent or a divergent p series? Pause. When I say class, I want you to call out either convergent or divergent. Think about it. Think p series. Class. Convergent. Is this a p series, 1 over n to the e? Is that a p series yet? Convergent or divergent? Pause. Wait for the word class. Class. Convergent, because e is greater than 1. It's in the greater than 1 category. How about n over e to the n? Oh, that's neither geometric nor p series. Kind of looks like p. It's got to be 1 over. By the way, if you had, instead of 1, if you had 18 here, you would just write that as 18 times the summation from n equals 1 to infinity of 1 over n to the e. Then this would still be a p series. Numbers pass through sigmas. Think of sigma as a semi-permeable membrane through which numbers can pass, but letters cannot. Now, let's go to the next page. We need to get the integral test. We have not done the integral test yet. It's time for the integral test, which detects both convergence and divergence. This is the 5th test of the day that we're looking at, and 5 tests in 1 day. Only 5 more to go after this one. Here we go. Integral test. This is it. Integral. Don't write integral test. They're all tests. Just integral, where a sub n is 1 over n plus 6. Keep in mind, the other test, nth term test, gives you no conclusion. It's not geometric. It's not telescoping series. It's not going to have that subtraction in it. And it's not p series. It's close to p series. In fact, if we weren't teaching the integral test today, we could say, oh yeah, it starts at 1/7. It's like it's harmonic series. It is harmonic series with the first 6 terms tossed out, right? So we know it's going to diverge. Just know that up front. But we need practice with the integral test. So here we go. Step 1. A sub n is greater than 0. Think about it. For n going from 1 to infinity, is 1 over n plus 6. Yeah, just check mark. Yeah, that's going to be greater than 0. Pretty darn convenient. Positive, decreasing. A sub n is decreasing. You don't have to do any fancy tests with derivatives. Come on. As n goes to infinity, the denominator gets bigger. It's decreasing. 3 A sub n is continuous. It's not continuous at -6, but we're not going from -6. We're going from 1 to infinity. There's no discontinuities there, so we're fine. So now the main action is in step 4. Step 4, let's look at the integral from 1 to infinity of a sub n dn. Because if the integral converges, the series converges. If the integral diverges, the series diverges. So here we go, let's roll. This is going to be the limit as capital A approaches infinity of the definite integral from 1 to a of 1 over n plus 6 dn. And that's going to be the limit as a approaches infinity of, we could do a u substitution where u is n plus 6. No point. We know it's going to be the natural log of n plus 6, evaluated from n equals 1 to n equals a. So we take, since we already know how to evaluate improper integrals, this is just a review. It's a natural log of the absolute value of a plus 6 minus the natural log of the absolute value of 7. This limit is in the form infinity minus natural log 7, which is infinity. So we say, I direct diverges twice. So the integral diverges. Therefore, sigma a sub n diverges. It's a two-step process. Step 4 says, okay, the integral diverges, therefore the series diverges. That concludes our lesson on the nth-term test, the geometric series test, the alternating series test, the p-series test, and the integral test. Assignments 8.2 and 8.3 are due on Friday.